Hey all, lesson 3.6, multiplication and inequalities. Learning targets today, you should be able to graph the solution to an inequality on a number line. This is a review of a learning target from last year in trans math. And number two, students should know that multiplying both sides of an inequality by a negative flips the inequality symbols. As we take a look, our first slide today is a kind of a warm-up in that it is a review, graphing the solution to an inequality on the number line. One of the things that we need to do is determine the boundary points. In order to do this, we're going to consider the inequality x is less than 6. At this point, you should come up with a few ideas of x's that work to complete this inequality truthfully. Here are a couple of samples. If we see, we can check them all out on the number line. Taking a look, these are some examples that won't work. Notice we have not graphed any of these on the number line. In fact, there is the one value that's going to separate the true from the false. That's right here at 6. That is considered our boundary point. If we're going to graph an inequality on a number line, the steps are pretty basic. Draw a circle around the boundary point. In this case, it is a 6. Shade the solution part of the number line. All of our solutions are going to be to the left of the 6 on the number line. We always need to determine if the circle should be included or if it should be left kind of as a force field just around the 6. In this case, it is not a valid solution. If I were to enter a 6 in for x, it would make a false statement. I always want to label my number line. The label is always on the right side to show that this number line represents possibilities of x. The exaggerated and shaded arrow over here on the left includes all solutions that are less than negative 12, like negative 100, negative 1 million, and so on. Let's check out another example. This time we would be graphing an interval. An interval because y is the set of numbers that is between, y here is between the negative 2 and the 8. This time we have two boundary points. We will draw a circle around both of those boundary points here at negative 2 and 8. We'll shade the part of the solution part of the number line happening here between negative 2 and 8. Shade the circle if it is a valid solution. This time we did shade in the 8. If I were to enter an 8 for y, negative 2 less than 8 less than or equal to 8 is true. I'm not going to shade negative 2. However, if negative 2 were entered, it would not make a true statement. I always want to label my number line again with a y. That concludes the review portion. Now we're going to get into the heart of the matter, multiplying inequalities. If we take a look, here are a couple of true inequalities. If both sides of the inequality are multiplied by 5, the inequality actually remains true. We call that the sense of the inequality, the direction, so it remains the same. What I'd like for us to do is just try multiplying both sides of a true inequality by a few different numbers. We want to keep track of the numbers. Does the inequality sense always stay the same? Our job is to determine when that happens. So let's just try another example. If the original inequalities are multiplied by a 4, go ahead and take a moment to do that. It appears that the sense of the inequality remains the same. Let's try multiplying by a 10. Again, the sense remains the same. What if we try multiplying by a 2? In this case, if both sides of the inequality are multiplied by 2, the sense remains the same as well. Multiplying by a negative 10. Ooh, this time we had to flip the inequality around, so the sense has changed. Just try a few others here. You can select your own, or you can follow with the ones that have been selected for you. In this case, you should be able to come up with some ideas for when the sense has been changed. They do have something in common, and we should be able to fill in the multiplication property of inequality. It has two parts, part 1 and part 2. If x is less than y and a is blank, then a times x is less than a times y. Part 2 deals with another option. If x is less than y and a is blank, then a times x is greater than a times y. Taking a look at our chart, the only time that a multiplication affects it is if the multiplication factor is positive or negative. The negative will change the sense, and the positive will not. This happens also when we are dividing an inequality. So let's take a look at a few examples. Solving an inequality is essentially the exact same as solving an equation. However, we have to be careful of the sense of the inequality if we divide or multiply by a negative. Here's an example. We want to solve and check and graph the solution on a number line. Here, we can see that it is a multiplication equation. We would divide both sides by the coefficient. Mindful, does the sense need to change? And in this case, since we are dividing by a -5, we do need to flip the sense of the inequality. So it becomes a greater than or equal to symbol. Simplifying out our common factors, we see that x is greater than or equal to -7. That is our boundary point. We will draw actually a filled-in circle in this one, and we would want to show values greater than or equal to 7. The check when we're checking our solving of an inequality is 2 steps. We always want to check the boundary point. Is this 7 the correct value? The boundary point we check for equality, meaning does it make the original statement a true equation, a true equal to. So if I substitute in a -7 for x, I would multiply, and I found out that 35 equals 35, which makes this boundary point accurate. I always want to check a sample value to test the sense, to make sure that my my inequality symbol is going in the correct direction. Here it says that x is greater than or equal to 7, so I'm going to pick any value that works there. I like to choose 0. It's an easy number to work with. Since 0 is greater than or equal to 7, and it will work for my check. Testing out an x equals 0, I find out that 0 fits into the original inequality, is less than or equal to 35. Another example, let's say that an architect is designing a building in which the foundation cannot surpass 150,000 square feet. If the length of the building is to be 300 feet, what are possible widths of the building? So I need to first set up the inequality. The area of the foundation has to be less than or equal to 150,000. Says that it cannot surpass, so it is not to be bigger than, it should be less than or equal to. Area is found by multiplying length times width. I know the length is 300. The width is the part that I don't know. I'd like to divide both sides by the coefficient, in this case a 300. Simplifying out common factors, it appears that we would want to have w less than or equal to 500. Now we can see that the sense of the inequality has changed here. That is not accurate. Since we did not divide by a negative, we would not change the sense of the inequality in this case. The width must be less than 500 feet in order to meet the qualifications for the building.